this Wednesday.
Today, we're going to
all those
do
numbers is like, no,
ECG.
laptop's available for everything else.
So we started talking about this a little bit so
Choose
far.
what you like
We haven't
for
gotten
that.
too heavily into it, but
Sick.
that's for today. So, first up, initial concepts that we've already sort of covered a little bit. The P wave is responsible for depolarizing the atrium, which means you're going to find that happening right before contraction occurs in the atrium. The QRS is responsible for depolarizing the ventricles, and the T wave is responsible for ventricular repolarization. Why don't we see repolarization of the atrium? It's hidden by ventricular depolarization. Your QRS is so big that basically the T wave of your atrial repolarization is obscured by the fact that it has such a big, strongly red QRS wave. All right, so this is the gist of what ECG looks like. We sort of have already, did you guys hear me okay? We have already sort of started talking about this. We covered the basic overall functions. Does anybody remember why the T wave looks the way that it does for ventricular? Yes, the way it repolarizes, even though you would expect that the first part of the ventricle to depolarize, which is the endocardial region, you'd expect that to repolarize, but it doesn't. What actually happens is the outer region, the epicardial region, starts to repolarize. Yeah.
Can you turn on your mic? It turned off up here.
Oh, it did?
You got the fan quiet. Whisper in the seats. Me too. Let me tell you about my aunt.
Better? All right. So, the appearance of the T wave is in the same direction as the depolarization, where you see it showing up above that 0 millivolt line. Anybody know what happens in atrial T wave if you could see it? Would it look the same as ventricular one? No. Which direction would it be? Goes down. Okay? And part of the reason for that, well, hypothesize that part of the reason for lack of a better word, the weirdness of the T wave for the ventricle is that the amount of pressure that is inside of the ventricles during the contractile period sort of forces those endocardial regions to stay refractory to repolarization for a longer period of time. So what we're actually looking at here is on the x-axis, it's showing us time, okay? If you were to look at an actual ECG sheet, would it tell you the number of seconds? Does anybody know what the number of seconds are? Or point 0.04 for the little section, right? The small squares. The large squares are 5 of the small squares together, which makes it 0.2. So that's what is actually being shown here. This effectively is each of these squares here represents 0.04 seconds. Okay? So this would in essence be the width of a large square of actual ECG mirror. So for ease, it actually has the numbers for seconds. It's a little difficult to see, but in this blue square, it walks you through specifically, what is happening in these tiny little regions in between the P and the QRS. So the SA node fires, which is going to start the initial signal that spreads throughout the atria, okay? It'll spread through the conduction pathway through the atria, but it will also spread to the muscle. When we're talking about the conduction system versus the contractile system, don't forget that your contractile myofibers have to depolarize as well. The only reason that you see this normal pattern is because the SA node, the AP node, the conduction system, including the interceptum bundle of His, the left and right bundle branches, as well as the Purkinje system, can spread the current faster. So it's a more efficient way to spread current throughout the heart. If you have a block within the Purkinje system, or within one of the bundle branches. It doesn't mean that you're not gonna get any depolarization on that side of the part. It just means it's gonna happen more slowly. Okay? Because let's say you had a left bundle, okay? You have a block at the left branch of your bundle of hoods. That means that the conduction system is not going to allow the left side to depolarize as quickly as it normally would, but the right side is depolarizing fine. Since your heart muscle functions as a syncytium, that current can still be sent to the left side of the heart. The difference is it's going to take a little bit longer because now it's going through the cardiomyocytes instead of through that fast conduction. So instead of getting this nice and tight QRS, you'll see a slightly wider QRS. Okay? So the amplitude as well as the shape of your ECG can tell you a lot of information about the overall function of the heart. So if we're looking at a standardized ECG, what does the RR interval tell you? Time between ventricular contractions. So how would you go about calculating the heart rate? Anybody want to respond? What's the heart rate between ventricular contractions? The interval we just talked about. RR, right? So if you're looking at the QRS and you're looking at the difference between the two, what is it about here? So it's actually about 0.8, right? So you're a little above 0.2, you're a little below 1.2. So you're looking at probably about 0.8. So that means 1 beat for every 0.8 seconds. How would you figure out beats per minute? You have to convert seconds to minutes, right? So what you end up with is 1 beat per 0.8 seconds, and then you would multiply that by 6. So you'd end up with about 75 beats. How would you do this if you looked at an actual ECG and these little numbers? Count squares, right? So you would count the squares in between each one. How many of those large squares would be in a minute? 300. Okay? So if 1 minute is 300 of the large squares, basically count the number of large squares between each of these. When we see an actual ECG show up in a little bit, you'll be able to look at the specifics. But effectively what you're doing is you are counting here. If this is considered one large square, you would count the number of those in this interval. Okay? 300 divided by that number gives you the value that you're looking for. See if I can find it. Just in case people don't believe in that. So, let's start with so we can start here, and we have basically 300 of the squares, right, equals 1 minute of time, okay? 300 of those squares, basically what you have is 300 squares per minute, and you're dividing it by whatever the number of squares is per beat. Okay, if you took these and you actually did to cancel out the squares, right? What you end up with is beats per minute. Okay, so if you had 300 over 4, you get about 75. See how that comes in?
Do you usually say is not about the RR interval?
So you could, yeah. That would be if you know the number of exact seconds between them. Yeah.
And to add on to what he was saying, that's what I was confused about, because you said the RR interval was 0.8, and then you said divided by 60.
No, times
60 was
It's
60 times
1 beat over one beat,
Divide by 0.8 times 60.
and then you would multiply by 60 seconds over 1 minute. So your seconds would cancel and you get beats per minute. Okay? So it just kind of depends on how you prefer to do it. Most likely, if I'm going to give you something where I'm going to ask you to calculate the heart rate, I will actually give you the time on the x-axis. That's more for your information to know what all the little intervals are in case any of you do volunteer or work in a doctor's office where you're actually going to work on ECGs, or if you decide to go for EMT training, that's something that you're going to be looking at quite frequently. So it helps to have a little bit of an understanding of how all these little lines are divided up. All right, so let's talk about the actual ECG itself, because this is going to be really important in understanding the mean electrical axis. Through a partially depolarized heart, the current is effectively traveling around 60 degrees. Okay? If directly due east is 0, and you increase as you move clockwise, this is roughly 59 to 60 degrees. That's typically what you would find for the mean vector for the current flowing through the heart, as it comes from really close to the entrance of the vena cava in the right atrium, passing through the atrial muscle to the AV node, and then down through the ventricles. The left side is going to be polarized a little bit faster than the right-hand side, but it spreads so quickly that effectively what happens is you get depolarization of both very rapidly, so that you get a combined timing of the contraction. Okay? You can have this angle shifted based on different conditions of the heart. What happens if you have hypertrophy in the right ventricle? So you have a condition that causes the right ventricle to become hypertrophy, which means that you have more muscle cells on the right side of the ventricle. The wall's getting bigger. It would actually be polarized faster. It's going to shift more clockwise. So you're going to get what's called a right axis deviation. This is considered normal. And one of the figures that you should have seen that was made available ahead of class is the actual chart with the angles, and it's color coded to show you what is the normal axis and what is considered right axis or left axis deviation. If you have hypertrophy muscle, it means the conduction will actually happen a little bit faster. You have more muscle, more connection, it's going to be a faster depolarization or a stronger signal depolarized on that side. So the right side would actually hold that mean electrical current a little bit more towards its side, which means instead of 60, you're looking more at like 100, 110. It would shift over to the right.
More muscle cells or larger muscle cells?
So hypertrophy means,
Bigger.
I'm asking, anybody know? We talked about this last semester. Hypertrophy and hyperplasia.
Trophy just means there's
Which one is-
shrinking. Plasia just means
Hyperplasia cells, hypertrophy is larger cells. So larger cells, less current. It's also larger number of cells. So when you get hypertrophy, you also get hyperplasia as well, because you get an addition of more muscle cells to increase the strength of the contraction. How they get bigger, but you also increase the overall size of the cells. So the current is actually able to travel through a little bit faster to get
this vector.
The plasia was the cells growing and then like the.
Plasia is multiplication, increased reproduction, number of cells. Hypertrophy means the increase in overall cells.
Shift towards the right side.
We use hypertrophy when we're talking about the overall muscle. It means the muscle itself is increasing. But on a cellular level, hypertrophy means an increase in size of that cell. Hyperplasia means an increase in the number of cells. But when we're talking about tissue, when you say you have hypertrophy tissue, you mean the size of the actual tissue itself. So the wall itself is getting thicker. It's due to a combination of having increased addition of more muscle cells, but each of those cells is also gaining a little bit in size, which decreases resistance, allowing current to be done really fast. We're going to focus mostly on the frontal limb leads. we will talk about the cordial leads, but you are looking at a 12-point ECG that we're gonna talk about today. So these 3 electrodes on your right arm, your left arm, and your left leg are giving you all of the information for the 6 frontal leads. Okay, so 3 of them are going to give you information about the frontal plane, looking at it from top to bottom. How is the conduction passing through, the current conduction passing through the heart from, I guess, north to south? The recorder is going to give you a cross-section, okay, from front to back. When we're looking at each of these, we have lead 1, lead 2, and lead 3, by definition, are your bipolar movements, because you are physically connecting 2 of the electrodes to your voltmeter. So your voltmeter is going to have the negative connected to one limb, and the positive is going to be connected to another limb. When we get to the augmented leads, that's a little bit different. So we're going to start with this first. The easiest way to figure out what voltage you'd be able to read at each point, at each one of these bipolar limb leads, would be to add up whatever the voltages are. Add up the 2 voltages from each of the electrodes, and that will give you the current that's flowing in that particular direction. Your lead 1 tells you information. I'm going to erase these arrows, but I wanted to point this out first. Lead 1 tells you information in this direction. Okay? Lead 2 is going to tell you information. And lead 3 is going to tell you information in this direction. Right? The Eindhoven triangle, which you should have also been able to see, will show you this and show you how everything kind of lines up. To start off, if we're looking at lead 1, which is in blue, the negative electrode will be the one that is on the right arm. The left arm will be your positive. You want to measure the degree of voltage that is being sent horizontally across the heart. Okay? So lead 1 tells you information effectively from west to east. Okay? So, if you took the negative 0.2 volts that you'd be able to read at the surface on the right arm and the positive 0.3, how do you get this value? How do you get the 0.5 being read at lead 1? By taking the negative 0.2 and the negative 0.3.
Final minus initial.
0.3
Final minus the initial.
minus the negative 0.2. Why are you subtracting them? This is a positive value, right? It's also attached to the positive electric lead. Okay, the positive electrode on that voltmeter is attached to the left arm. Okay, so you are adding up the voltages that will be measured at the surface of each one of these individual electrodes. We have to keep in mind which sign it's plugged into. On the left, we have a negative sign that is attached to a negative. So you take whatever's on the right and you subtract whatever's on the left of this chart. So 0.3 minus the negative 0.2. And you can do the same thing for leads 2 and leads 3. If we were to look at lead 2, what do we have here? The positive is connected to, right? Positive. The negative is connected to the negative 0.2. So what's the end result? 1 minus negative 0.2 gives you 1.2. That's the voltage that you're going to read at that lead. Now, we talked already about the difference between the little versus the large squares, but only on the horizontal axis. That is your time. What about the little ones? What would be large square in the vertical axis of the half a millivolt. So if you were to look at lead 1, basically your QRS spans that one large square. So you can figure out the voltage that's being measured in each one of these leads just by counting the number of large squares that QRS is marked. Okay? So baseline about 1 square. Same thing here. You're starting baseline, going up about 1.2. What about for lead 3? Lead 3 gives you what? Positive is attached to where? Positive 1. And the negative? Positive 1. Positive 1. Sorry. Wrong one. Positive 3. So how would you solve for that to get that 0.7? You got to pay attention to the fact that your negative is the one that's attached. Okay? And your positive is the one that's attached. Okay, so the positive lead minus whatever the voltage is, right, picked up by the electron of the connection. That would give you the readout here. That's just a little bit of basic stuff, how the overall thing works. Typically, you're not really going to be worried about measuring specifically what's happening at each one of the individual points of the pin, because what you're looking at, you're going to look at how to read the actual ECG readout. But this is how your bipolar leads work. It's a little bit different than what we see with the augmented loop. So right now, we're looking at a triangle. It's an equilateral triangle, right? So your 0 degrees, your horizontal, is going to be for lead 1, right? What about for lead 2? What angle is that? Red. Positive 60, okay? 60 degrees down, it's in the positive direction because as I said, you're starting at 0, which is due east. You increase the number for the degrees, positive number starting clockwise from that point. So 60 degrees for lead 2, what about for lead 3? Purple. Remember, 360. So if you went 60 and you went 60 more, 120. Okay? That's actually what we're looking at here. This is Eindhoven's triangle. Wilhelm Eindhoven won the Nobel Prize in 1920 for his discovery of ECG. So this has been around for a really long time. And it's basically predicated on the fact that you are bathed in an electrolytic solution. So current is conducted here. You are not actually measuring the current that is flowing through your heart. Okay, it's important to note that. When you're measuring for your ECG, you are not measuring directly what's going on inside the heart. You are measuring the current flow as it's received or perceived by the skin on the surface. It's a non-invasive procedure. Okay, but it's based on the principle that your body is filled with a highly conductive fluid. All right, so lead 1, lead 2, and lead 3. This is basically what we saw on the previous one. Those are your bipolar leads. You also have augmented leads. That's your AVR, AVL, and AVF. What AVR, AVL, and AVF does is it bisects the 60-degree intervals that you can get for leads 1, 2, and 3. These are also called your unipolar limb leads. And they are calculated by taking the positive electrode and connecting it to one of your leads. So if we're looking at AVL, L is for your left arm. I'm learning how to color. AVF is actually for your left foot, your left leg. Okay? And AVR is for your right arm. So the letter on the augmented lead refers to which limb the positive electrode is in. What about the negative? It's actually essentially the electrical need of the other two. So, for ABF, the positive is the lead from your electrode on the left foot is directly attached to the positive for your ABF. Okay? The negative takes the average from the right arm and the left arm. It defines it as the electronegative center of the heart. By averaging the other two limb leads, effectively what you have is the negative. Okay? ABF means that the positive electrode is the one that's reading from the left leg. Right arm and left arm together define the electrical center of the heart. For ABL, you're going to average RA and LL in order to get that negative side. The positive lead will be attached to the left arm. Same thing for ABR. ABR is going to tell you the direction of current flow that is traveling toward the right arm. The electrical negative of the cell is going to be the average of the LA and the LL. Should we see a lot of current going in the direction of ABR? It's measuring the positive direction of current flow, the depolarization. Should it travel toward your right atrium? No, because it should originate from there, right? That's where the SA node is. So you should have current starting up there and heading down toward which lead should normally have the strongest positive depolarization from all 6 of these. Remember the number I told you, the typical average ES, cardiac S? Roughly 59 to 60, which makes it okay? These two should have a very strong positive deflection of your ECG because under normal circumstances, your cardiac axis should roughly head in the same direction as you too. And it's measuring the depolarization of current that is passing through that direction. So all of these together, you only have 3 electrodes, but you're measuring 6 different angles. Effectively what this tells you is every 30 degrees or 360 degrees you get information. How does this translate to an ECG? If the direction of current flow is going toward the positive electrode that you are measuring from a particular lead, you're going to see a positive deflection. Okay, so lead 2 should have a very strong positive deflection because it's measuring current in the same direction the current is actually. ABR should have a very negative deflection. So if you look at your QRS on ABR, you can see a negative deflection for that shape. And the main reason is because it's actually traveling in the opposite direction of where ABR is measuring.
I just wanted to clarify, you said at 360, a triangle is 180 degrees, so where are you getting 360 from?
Because you are bisecting all of these. Actually, how do we just go this one? And I guess I'll have to do this. So one of the things that you got was a colorful figure that shows you the wheel of 360 because basically extend that 180. And if you were to take these and sorry, but if you were to take your angle here and your angle here, and then what if you took lead 3's angle and instead of having it here, you put it here, then you can extend these to see how you get that full 360. Okay. So that's going to show up in just a second. I'll delete all that next. Yeah. No, that's coming. Okay. So, what we have are, stop off. Okay, lead 1, the axis is 0 degrees because it's measuring the horizontal direction from the arm to the arm. Your second one is right arm connecting to left leg, and the lead 3 axis we talked about was measuring from your left arm to your left foot. It's effectively that 120 degrees. these are the angles that we're looking at, and how do you see the same signal being read at each one of these leads? When you have a positive deflection, a major positive deflection, that means that the current that that particular lead is measuring the same direction that the actual current is flowing apart. So because your normal current is going to flow toward this direction, it's normally going to flow in this direction, you would see positive deflections in several of your leads, especially in your ADF as well. You don't see that in AVR. In AVR, you see a negative deflection because the current is actually traveling mostly opposite from what is actually being measured by AVR. AVR specifically is looking at how much of the current in the heart is flowing toward the right arm. Almost none, okay? You shouldn't have a positive deflection showing up, or a very strong positive deflection showing up in AVR. It should be mostly negative, because most of the current flowing in the heart should not go back toward the source, which is the okay. The important thing to distinguish your ECG is looking at what each of these leads is measuring. The lead itself is only giving you information. If you look at one lead, it's telling you only information about the direction of flow, how much of it is happening in that particular vector. Okay? Your precordial, we're not going to spend much time looking at these because I think it's going to be enough just to have you measuring your cardiac axis, looking at the 6 polar leads. But the precordial leads are there to give you that cross section. So leads 1, 2, and 3, AVR, AVL, and AVF, they're going to tell you the y-axis. The precordial is going to tell you the x-axis, or the z-axis. So V1 and V2 are really going to sit. You place them at the 4th intercostal space at either side of the sternum. Then V4 and V6 are going to be placed at the 5th intercostal space at both the mid-clavicular line for V4 and then the mid-axillary line for V6. V3 and 5 are just spaced in between 2 and 4, and then 4 and 6. Okay, so you put it at the midway point. And what happens is you get the front, this is the front of the body, this is the back of the body. Okay, so you're measuring V1, 2, 3, 4, 5, 6, measuring all current heading toward the front. Because of the way that your heart sits in your body, it should normally be heading in that direction. If you have mild infarctions that will affect the conduction system and force the current to go through the myocytes instead, you'll see some delays in the way that each of these precordial leads are going to be able to read the current that's flowing. Okay? So it's important to know that these are the other 6. You actually have 6 electrodes to measure the precordial, whereas you only have 3 electrodes to measure the 6 different angles that you can read from the bipolar wave. Right, so it's a 12 lead ECG, 6 in the vertical plane and 6 in the horizontal plane, but you're really only using 9 electrodes to read. Now, anybody ever had an ECG? Do they put something on your right foot? You know what that is? Your left foot. So, if you have an ECG, they're only really collecting information from both your arms and your left leg, but your right leg is the electrical ground. Make sure that you're only measuring changes that are happening inside of the leads and reading the body. Okay, so this is what I was talking about not too long ago. This is the angle, the 0 for angle lead 1, the 0 degrees, lead 2, lead 3. In blue, you have your 0, 60, and 120. Because if you took this blue one and you put it over here, drawing over the triangle in blue. The augmented leads are basically taking what we already saw was in the middle of Einhorn's triangle. Right? We saw we had this. Down. And you are taking the center and just shifting it up to get here, here, and here. Okay? So when we saw Einhorn's triangle in the context of the torso on that previous figure that was from the Boron book, this is looking at it if you took all of the negative ends of those vectors and you place them all at the single point. This is how you'd be able to see that full 360 degrees. So it's the same thing as what we saw here, just with all, I guess, the butts of your arrows at one point and showing what the directionality is of each of these. So AVR, the negative would be down toward the left. That's at about 30 degrees. Positive 30 degrees is where the negative end of this vector is. And then the positive is up at 210. AVF goes down to about 90 degrees because that's the positive vector. You would have 270 for where the negative is. AVL would be either negative 30 or 330, depending on if you want positive or negative values. And then the negative 1 would be down another 60 degrees from 90. If you add in 1, 2, and 3, and you extend all of these arrows, what you really need to pay attention here, this is what we're going to use when you're looking at the actual ECGs, is pay attention to where the negatives are. Because the one we showed before was only part of it. Extending all of these vectors shows you the direction of the negative value of that vector. So this would be, if you had a normal QRS, very strong negative deflection, it's basically going to be, the cardiac axis is going this way, AVR would have a negative deflection. Because the actual current flowing in the heart is traveling in the same direction as the negative electrode by definition of that AVR. How many people remember vectorial analysis? So, that will help when you start looking at the positive and negative deflections, trying to figure out if you should see one or both or none for a given speed. Typically when we talk about your cardiac axis, I think it's, I want to say it's chapter 12 in the guidance book, does a really good job of walking through vectorial analysis. Specifically, how you go about taking a specific, this is your XY axis, and you have, oh, sorry, and you have a vector here. How would you go about figuring out the components of that vector? How do you know how much is going in the x-axis versus the y-axis? What do you do? Yeah, but how would you actually draw the arrows that are part of that vector, the components of that vector? Yeah, but how do you know how far? How long, right? Because the length of a vector is magnitude. The arrow tells you direction. So how do you know how long the corner is? Hmm?
So labeling the axis to understand what the values are, right? Because then you can figure out.
Very simple question. We're making it a little bit more complicated. Just looking at drawing those straight lines down to make it a right angle. And then you would use your function. But not everybody may have had physics or had physics in a long time, so I'm going to have to be very easy. So from the end of that vector, draw that line straight down. He's exactly right. If you wanted to know exactly what the component was, you do sine, cosine, tangent in order to figure out how long that side is, okay? But in order to know what it is, you need to be able to draw what the vectors are that make up that resultant event. Okay? Chapter 12 walks you through how to do this on a number of different examples. You're not going to be expected to do this specifically. It'll help you when we start going through the cardiac axis. Okay? The reason for that is because when we start looking at an actual ECG and lining it up with this example, you'll get some version of this. It probably won't be color-coded because when I make copies, it's all black and white anyway. But you will get some version of this showing the different angles on an exam. So you'll get this next to an ECG to be able to tell me what the cardiac axis is. The cardiac axis is the same thing as your mean electrical axis. What direction is the overall current going? So how would you know, based on when you're looking at an ECG, how would you know how to figure that out? There are a couple of different ways to do it. One of which uses that vectorial analysis by looking at leads 1 and 3 and solving for the resultant vector of leads 1 and 3, and that should give you a pretty good example of what you find. You need to measure and know exactly what the voltage is, the exact length of that magnitude in order to get the proper resultant vector. Okay? There's an easier way to do it that gives you angle without having to actually measure everything. The first thing that you want to do is when you're looking at the 6 leads that we talked about, you want to find what is by definition the isoelectric point. It's also called the equiphasic point. And the cardiac axis is going to be roughly perpendicular to whatever the isoelectric or equiphasic point is. So you want to find something that has either a very low voltage being read or roughly equivalent positive and negative differences. That, by definition, is your isoelectric point. And part of the reason for that is that if you look at lead 3 is going to pass in this direction. If this is your positive and this is your negative, for lead 3, why would you see a positive deflection and a negative deflection for the cardiac axis? What does that tell you about the component vectors that are playing a role in the actual flow of current?
Well, you have the current coming in through the ventricular septum, but then you have it coming back up from the outside of the ventricular wall back up toward the atrium.
Yeah, so it's going to come down through the septum. It's going to angle slightly toward the left ventricle, and then it will radiate out toward the right, and it will come up through the ventricle. So what happens here is if we're looking at this angle, if you're going to have a positive deflection, that means that some of the current is traveling in the same direction, right? And some of the current that's being measured is traveling in the opposite. Okay, that's why you have a positive deflection that's being read there. That's responsible for the part that's above the 0 point, and you have some negative current that is being measured as it flows through the ventricular. So, if you had a normal, let's say your actual cardiac axis is somewhere here. Okay? So if this is your cardiac axis, what would be your the component vectors of your cardiac axis? Which direction? North, south, east, west. South and east, right? So if you're looking at the component vectors here, you have an eastern vector and you have a southern vector. The southern vector would be responsible for which? The positive or the negative deflection? They're traveling in the same direction. What about this component that's heading away from the 3? That would be responsible for the negative. Okay? And that's why one that is perpendicular, when the actual cardiac axis is perpendicular to a particular lead, you will see either nothing. It'll be very low and it'll actually look like there's nothing being measured there. Or you will see a positive and a negative deflection because they share one resultant vector, but not the other. Because if you were to do the resultant vectors only of lead 3, you would have this shared one, and that one heading the opposite direction of what the lead is. So one is shared in the same direction, one is not. So you get a positive deflection for the shared vector, and a negative deflection for the unshared vector. Okay, so that's why that's your starting point. When you start there, that means lead 3 is roughly perpendicular to the angle of your cardiac axis. So, what is perpendicular to lead 3? Looking down here. What's perpendicular? AVR, right? So now, we're going to look here. What does AVR show? Large negative deflection, which means the angle of the current flow as received by AVR is headed in which direction? Toward the positive electrode or the negative? If it's a negative deflection, it's going in which direction? Roughly what angle? What's this side? Is this side over here, is this positive or negative for AVR? Probably can't see it very well. Get rid of my circle. This is where the point is. If this is where the arrowhead is, the arrow is always pointing toward which electrode? Positive or negative? Positive. Okay, so if this is the positive for your AVR, if current were traveling in that direction, what type of deflection would you see on the AVR readout? Positive. Well, we see negative, which means it's heading in which direction? Toward the negative end of that AVR, which means a good estimate right at this point would be roughly 30 degrees. Okay? Now, you can take it even further to estimate plus or minus 15 degrees based on the actual magnitude of the deflections that you see at the two neighboring leads. So, one neighboring lead for this putative, in fact, this is your putative cardiac axis, okay? So the putative cardiac axis would do about 30 degrees, okay? What are the two neighboring leads? 1 and 2. All right, so now we're gonna look at 1 and 2 up here. Now, it's a little hard to see on this screen, but if you were to look at the magnitude of these peaks for your QRS, so the peak of the R, is there a noticeable difference between the two? Not a huge one, right? They're pretty similar. There's a slight difference, but they're roughly similar. Which means that both of them are measuring roughly equivalent deflections due to that cardiac axis. So it's pretty much equidistant. So that 30 degrees is actually a pretty good estimate for this one. What would happen if instead you saw a small lead 1, small lead 1, compared to a larger one on lead 2? The axis would be closer to 60 because lead 2 would be more closely aligned with the directionality of that cardiac axis. So if you have a greater deflection, that stronger signal is being measured by lead 2, which means this would actually shift to about here. And then you would have an estimated one about 3. Okay? It's not going to give you the exact, that's supposed to be, that gives you a good estimate of what you would find for your cardiac axis. Okay? Roughly speaking, you can figure that out looking at just those 6 little leads in order to determine about where your cardiac axis is going, based on the shape, the size, and the directionality of the 6 leads. How do you guys feel about that?
Can
you explain how you got the other arrow going off of AVR?
Oh, yeah, so that is because we have up here, in AVR, we have a negative deflection. And AVR, this is the positive end of AVR, this is the negative end down here of the AVR. That vector has the negative electrode, we're basically measuring current starting from the negative, heading up toward the right atrium. So looking at it, it would be heading in this direction. So because there's a strong negative deflection, it means it's measuring current, but it's measuring current traveling in the opposite direction that this electron is measuring. It doesn't measure current going this way, but current traveling in the opposite direction. So that's where that black arrow came from. Because it's basically a negative deflection means that you should follow the negative side of that.
You say that, lead to always shows up as your negative deflection,
Stronger what? Sorry.
a stronger negative deflection.
No, positive. So if you have a normal healthy heart, it would be a stronger positive deflection. Because lead 2 is at 60 degrees, and in a normal heart, the average is about 59 to 60 degrees. It can be anywhere in that red area, okay? So you actually do have about 120 degrees that are still considered normal before you technically get much into that left to right axis deviation. But that lead 2 is effectively measuring your cardiac axis. So it should have the strongest positive deflection because it's directly measuring almost exactly where the current should be going. If it doesn't, then you have some kind of conduction issue with it that should. Now, it could also be that your normal cardiac axis is based on the anatomy or based on the shape of the heart or where it's sitting in the body. It can also shift a little bit. You can have right and left axis deviations based on position as well. All right, so how are we so far with this? Okay.
So I know that if the peak increases or decreases, it can show there's a difference in the cardiac axis, but if the width of the QRS changes at all, does that show a reflection of the change in axis?
So the width of the QRS has more to do, not as much with the cardiac axis. It does a little bit, but not as much with that as it is, it's telling you about how that current is being spread. Not necessarily changing the direction, but if you have something wrong with part of the Purkinje system, then the current is still going to get to that part of the heart. It's just going to take a little bit longer because now it's passing through the muscle fibers instead of the conduction. Any other questions? Okay. So this is from the guide, I think it's actually from that after. This runs through a little bit about the vectorial analysis so that you can kind of get familiar with it. I put this up so that you know what you're looking for when you go into the guidance book. I'm pretty sure it's chapter 12, but I can't remember if it's 11. I think it's 12. But this will run through what we sort of talked about before, where you're looking at the different components that can be measured specifically at each point. So if you're looking at, let's say, you want to look at B. We'll start at B, right here, okay? You'll notice that if you were looking at these actual deflections on a regular ECG, you would be able to use the number of large boxes to estimate the actual voltage. So the reason for these different 1, 2, and 3 leads, that's telling you information specifically based on the deflection degree, the magnitude of that deflection, which is why the vector for V1 and the vector for V3 are similar in size, but V2 has a much larger vector. Remember, for vectorial analysis, the arrow tells you direction, the length tells you magnitude. Okay? I'm not going to have you do this on a test or anything, but it does help you to understand those components as you're starting to go through looking at ECGs to be able to measure the cardiac axis. All right, we've got about 4 minutes left. So, few causes for having some arrhythmias. You can have the pacemaker has either an irregularity, or you can have a regular irregularity. It is possible for the normal conduction of the heart to have an irregular heartbeat that occurs at the same time. So every third beat to be a regular irregularity. There are a number of different causes, and sometimes that's just normal. You could have a shift from the pacemaker from the sinus node. If your sinus is no longer the fastest part firing in the heart, something else is going to pick up. What's next in line? The AV node. What does that have? Purkinje system. You could have something that is hyperactive in the atrium or in the ventricles, and you could have ectopic pacemaker. But typically, the normal ones that have those slow waves are going to be your SA node, your AV node, and the Purkinje system. You also can have blocks that are at different points in that transmission, and abnormal pathways, which means some kind of shortcut. If there's a short circuit, and not all of the current is going in one direction, there's a way to depolarize part of the heart faster, and you will see that show up as an arrhythmia. Spontaneous generation, that is the ectopic sign. So, tachycardia just means what? Fast heart rate, okay? 100 beats per minute or above. Bradycardia, slower heart rate, okay? There are a number of different causes for each of these, but it's important to understand what these terms are so that when you get a clinical vignette on an exam that says the patient comes in and this is their heart rate, you should know if that's tachycardia or bradycardia, and that'll help narrow down what might be going on. If we're looking at sinus rhythm, normal sinus rhythms on top, this one I believe is from the Muddy book. It just shows you how they would line up next to each other for sinus tachycardia and sinus radius. This means that you specifically are speeding up and slowing down the heart rate based on speeding up or slowing down the rate at which the SA node is firing. So it's not due to a conduction problem, it's due to a change in the firing of the SA node, which a lot of times can be sympathetic comparison. If you have sinoatrial block, if your SA node is not firing, you don't have what? T waves, right? No SA node means that you're not going to have that depolarization preceding the QRS. The next in line is your AV node. Your AV node is now your pacemaker. It will still depolarize the atrium, but now it's going to be sending signals in both directions. So you're not really going to see that depolarizing of the atrium because it's going to be obscured by that QRS. All right, heart blocks. An incomplete heart block, your first degree, just means that your signal still gets through the AV node. So you have a first degree AV heart block. That signal from the SA node and the atrium is still going to get to the AV node, just not as quickly as it should. What that means is that your PR interval is going to be a little bit longer than that. So the depolarization of the atrium and depolarization of the ventricle will just happen a little bit more slowly. So if you have that prolonged PR interval, that means first degree. And we're at 11:30. Do you guys want to cut out? It's my fault that we're running behind. I know some people have time for that, so we can stop right now. And we'll finish this up on Thursday. It's only 15 slides.